Hi, everybody. Welcome back to the realm. I'm Gina.
And I'm Rich.
So welcome to our Monday deep diving topic. Every other Monday, we bring to you just a single topic that we try to take a closer look at certain topics. I know every Wednesday we do our Weird Weekly News with a couple newscasts, but this is some of our favorite work here. So today we have a huge treat for everyone. If you remember, 2 episodes ago, we did Cern Part 1, and this is going to be Cern Part 2. So I'll recap that episode here briefly, but Rich, are you excited?
I'm looking forward to it. I remember the first episode we did when we talked, and we kind of got going, and it was hard to stop.
I know, so I can't wait to hear from this guest today because I feel like she will get us on the path.
Sure.
Path. So the guest that we have today, you guys are in for a real treat. She's been on other podcasts discussing many things regarding CERN. I've been able to listen to these podcasts. She's done interviews and so many other things. So our guest today is an experimental particle physicist at INFN, which is the National Institute of Nuclear Physics in Padova, Italy. She specializes in analyzing data that comes from particle collisions. And during her 20-plus year experience, she was part of 2 very important discoveries in particle physics. Rich, she was part of the discovery of the top quark at Fermilab and in 1995, and the Higgs boson at the Large Hadron Collider in Cern in 2012. So
exciting!
Really, if we're gonna have anybody on the show, that's who we need.
Absolutely.
So currently, she is with her career, she's focusing on the design of the new future colliders. One of these ambitious projects is the Future Circular Collider at Cern. If you remember last episode, we talked about how, they're going to build an even bigger one.
Right.
And so it's going to consist of a 100-kilometer, which I looked it up. I had to 62-mile tunnel. And that will first host an electron-positron collider, and then followed by a proton-proton one, which will reach 10 times the energy of the current LHC at CERN. Can you imagine? So imagine the theories that are come out then. Along with her colleagues at CERN, they're trying to decide what characteristics this new generation of collider is going to need to better understand the data they've already collected with their current experiments. And also, what are they going to detect next? And will it include new particles that could be considered dark matter? So, of course, I need to mention that Patrizia is also the proud mother to 3 incredible children. She's also been a friend of mine for over 20 years. I have to put that shameless plug in there. She also is an extremely talented person. She has lots of interests. She's a yoga instructor. She's a talented pianist. And she's engaged in programs at something called the Empowerment Lab that inspires young girls to pursue science, technology, engineering, and mathematics studies, which is also known as STEM. So last but not least, let me just welcome to the show. Let me name our mystery guest is Dr. Patrizia Azzi. Patrizia, welcome.
Thank you. Hi, thank you for having me here.
Thank you for being here.
Thank you for the introduction.
Well, I mean, I feel like I could not encompass everything that you are in this brief introduction, and it's the longest introduction I had, and it doesn't even scratch the surface of how talented and amazing and brilliant you are. So I want to say thank you so much for entertaining our podcast by coming on the show. It means a lot to us that you would do this.
Yes, thank you.
My pleasure. Thank you for inviting me.
So I know that I had sent you the last episode and you had a chance to look at it, and we're going to dive into that here soon. So first, what I want to do is give you the opportunity to talk a little bit about the history of this experiment at CERN. So this first started at Fermilab National Accelerator Laboratory in Batavia, Illinois. So could you briefly explain the difference between the experiment that was done at Fermilab and CERN? Because they're kind of the same thing, right?
Yeah. So first of all, just as a nitpicking, you call this experiment. So this is not an experiment. We are talking about 2 different machines.
Okay.
And at the machines, we do many experiments.
Okay.
This is not just you. I mean, this happens often, even in the first page of magazines, whenever we start the LHC. I remember in 2010, it was like, the experiment is starting today. And
like it's a singular thing. Result?
It's like, wait a second, we haven't even started. So we're talking machines. What do we mean by machines? These are called particle colliders. So they are basically circular tubes where we make our favorite particles that we have on hand. So in Fermilab, it was protons and antiprotons. And at Cern, it's just protons against protons. And then we make them collide into each other. And then the experiment is, in fact, what we call the detector. So it's like a very sophisticated camera, if you want, that takes picture of what happens during the collision. And in fact, there are multiple experiments on these machines because the machine is expensive and complicated, etc. So in Fermilab, we reached an energy that was enough to discover the top quark. So basically, just to make it simple, we make very large use of the Einstein equation, E = mc squared.
Okay.
So basically, if we want to create a very massive particle, we need a lot of energy. So the energy comes from the beams, they collide, and at the moment of collision, the energy can be used to make a new particle. So this is also what brings us, back to being very close to the Big Bang. And that's why, we're particle physicists, we study the fundamental laws of the universe. So at Fermilab, we needed that energy. It was a very, very great machine for the time, for its time, because it allowed to create that. And just to give you a feeling, we had, in the end, very few top quarks in the beginning. When we made the discovery, we had about, I think, less than 100 in our measurements. Okay, it was difficult to make them. So then people at the, more or less at the same time, decided to make another machine at Cern, and actually the history is a little bit more complicated because the tunnel at Cern was already built for a machine with different particles at the time. It was called LEP, Large Electron Positron Collider, with electron and positron. It was running more or less at the same time of the tevatron, slightly before. So they were doing specific studies. And then, since these tunnels are very expensive and complicated to make, then, you repurpose. So you scrap out the plus minus and you put in the new system for the protons.
Yes.
Right?
Yes.
So, we use things. We don't throw away stuff. We reuse it.
Right.
Right.
And so then we started, and that was changed the name. And so that became the Large Hadron Collider, because we made protons run in the tunnel instead of the electrons. And at that point, with that machine, there was 27 kilometers. The one in Fermilab, if I'm not mistaken, is like 3 miles or something.
Yes, that's what I remember.
Anymore. I didn't check the number, sorry, but it's much bigger. And then when you have the protons in this bigger radius, plus we have bigger magnets, bigger everything, to get a higher energy. And so the energy of the LHC now is about 6 times the one that was at tevatron. Okay, as of today, we are about 14, 13, and at Fermilab it was about 2 TeV, which is this unit that we use. I'm not going into details, but let's say it's 6-7 times higher energy, and then again the setup is very similar in the sense that we have these particle collidings, and it's a circle. So then we can have many places to measure what happens. Being bigger, being more expensive, being, then we can have more experiments. And so we have 4 experiments at the LHC. We had only 2 at Fermilab. We're going to have 4. We have 4 here. So 4 the big detectors that take pictures and measure what happens. Yeah, and so the difference is that with this higher energy now, then we can go closer in time to the Big Bang, because energy is like temperature, and so we go closer to the beginning. And it's good to be closer to the beginning, because in the beginning the particles are all free. Now then everything got cold, and then particles stuck together, and we had matter, right? Okay. So we have more energy, and then we can create possibly more massive particles, or particles that are harder to make, like the Higgs.
And that's where people become afraid. That's where the people who don't understand science become very afraid. Exactly. And that's okay in the sense that not all of us, because honestly, just because I was a slight science nerd, I say nerd lovingly because I proudly wear the badge, but I loved science. And in fact, I remember when I said in the first episode, when I finally found out what you guys did after hanging out for months in my messy apartment, I was just like, oh my God, I forgot to roll out the red carpet, because I think it's so amazing. So essentially, we're talking that it's all similar, but just the power at Cern is just greater. It has a bigger space.
Exactly. To be able to... It's the next level. It's higher energy, basically. Higher energy, and actually it's not just higher energy. It's higher everything. Is also more frequent collisions, more experiments. It's more.
And more scientists working on, I guess on average, I know. So first of all, I wanted to thank you for kind of putting into perspective that it's not an experiment in and of itself. It's a machine that's running many experiments. So I appreciate that. Mm-hmm. And having said that, I guess if you had to guess, and this wasn't something we discussed before, how many nations or scientists do you think are working together at Cern to dive into this subject?
Well, okay. So let's distinguish the LHC and CERN.
Okay.
So the Large Hadron Collider, and we have 4 experiments, and you should imagine that the 2 biggest ones, so CMS and Atlas, the one that discovered the Higgs, to say, if you don't know the name, they have they've been growing as collaboration, and I think now we are around like 6,000, 7,000 scientists each. Okay, wow. Where everything included, like from senior scientists to students, technicians, engineers. But it's a large amount of people, and they come. Yeah, it's complete international. I don't know. It's like 200 countries. It's a very large number of different countries and nationalities. There is really we live the meaning of a peaceful science, a peaceful collaboration for science. So we all speak the same language, and so there is no religion, no sexual orientation, no country. Of course,
that's beautiful.
Actually, yeah, and it's beautiful. I mean, right now, in fact, it's a tough time, and this is not maybe the space to get into that. But of course, given the situation in Europe now, even scientists are doing a lot of discussion about how do we separate or not, the desire for peace and giving the right to our friend scientists from every country, including Russian scientists,
right?
In a moment where you have ethical concern. And so it's a very difficult discussion.
It's a delicate topic, I would say, but I think
very delicate. And I'm also in international committees discussing these things. It's really, really delicate. And so it's not the subject for this.
Right. One. No, but
it's good to keep in mind.
I think it's important that you bring that up, though, the fact that how phenomenal it is that you have this international organization trying to achieve the same goal, and everybody's working together.
It has to be that way, I think. That's the only way.
Absolutely.
That's the only way.
And we care about it very strongly. That's why there is a very strong push from a scientist to always be more allowing the scientific work and trying to be separated from whatever is not science, which is politics.
Right. Which is politics, right?
Yeah. So in fact, CERN was built after the Second World War. It was built in 1952 And Cern itself is not just a Large Hadron Collider. Cern is a big laboratory in Europe, and it was really born after the war for scientific purposes and for peace. And in fact, something that, okay, I wanted to say it at the end, but maybe I can say it now.
Yeah, say it now.
Concerning conspiracy and everything, I'm also a CERN guide, and we have many experiments. We at CERN we study the fundamental laws of the universe, and also lots of applications. There is no secrets. There is no military project. It's all completely open. It's funded by the citizen, so anyone can come. We have open visits. People can take pictures everywhere. They are not allowed in places sometimes just because maybe there is a danger, and I don't even go there, so nobody.
Yes.
Because if it maybe a place where you have radioactivity or whatever, but it's completely open, and I think this is very important for anyone that is curious and not just maybe following the latest conspiracy. If you have an honest question, we all have them, and the best thing is just to call, come, visit. There are also virtual visits, and so I think this is also very, very important to know. And maybe this is something different from the US, where the labs are also government funded, and as much as they are open, then not all of them have the same rules as here. But CERN is a very good example where by construction it's open, it's available. There's no words.
And that's why I have to say, so I'd have to digress to my first one where you and I had discussed after you listened to our first episode, I had made a comment, where it's like, I definitely need to clarify. It's not that the secret, it's just some things you're not able to, like, maybe it's not on my level to understand. And all of my memories are from, 20 plus years ago. And in fact, I did get to walk around Fermilab, and I did get to go to CERN, and unfortunately I couldn't go where we originally planned for me to go to visit things near the collider. I think there was an issue with the magnet. Correct me if I'm wrong. I think there was something going on that day. And so we got the phone call at your house, and I was like, oh, but we still went and we got to visit, and it's a pretty great campus. But so let's dive into these theories. What do you guys think?
Yeah, let's revisit a couple of those and see what the real
what the real story is.
Yes, that's probably the real story. Not the conspiracy part of it.
I know, right? Well, and like I said, we believe here at the Realm, and I think in general, I think Rich, you and I think much the same way, that we think it's super important for people to question things, right? Mm-hmm. Believe in the possibility that we can't always trust what we see. There's things that, we just never really know what's really out there. I feel like, Rich, I don't know if you feel the same way. Nobody really has all the answers to life and beyond. So
I would agree.
Keeping an open mind and listening to all the theories to consider what if is important. So I definitely don't want to shame anybody that has questions or has any of these theories. We just think it's important, though, to be responsible, that if you're going to question, we need to look at all sides. And Dr. Azzi, that's why we are speaking to you today. So we will go theory by theory on these things that we found on CERN and the conspiracy theories. And so we'll kind of recap the ones that we went through. And so kind of what happens is there's some people that consider themselves, I'll have to say, like, quote, or spiritual leaders. And they believe that the Large Hadron Collider was actually designed to prevent our species from evolving into the fifth dimension, which is kind of like a spiritual belief system that some spiritual leaders have. So, in fact, some people have gone so far as to say that some scientists are covering things up, and even saying that some scientists themselves are being duped by a higher level of government that holds all of these secrets and knowledge that come from alien technology that's been discovered, or communication they may be having with intelligent alien life, or secrets that are just passed down about the universe to a privileged few that have a sinister plan in place. So I'm sure you'll be able to answer as to whether or not. So I guess, do you feel duped as a scientist? Let me start there.
No, I don't think I feel duped as a scientist. Yeah, I think some of this always comes again. Sometimes I think there is a desire that some things are secrets, and the point, in general, this is also something that sometimes conspiracy people don't think about. Scientists are very open-minded and they're very curious. I mean, I'm doing this job because I want to find maybe new particles. I mean, maybe I won't find them, but I'm trying to discover different things, maybe to figure out new theories for what we understand. Now we have a beautiful theory that works perfectly, but we know that it cannot be enough. We know it's not enough. We don't know where dark matter comes from. This is not hidden. This is known. I mean, dark matter is like 90% of what is out there.
Right.
And it's not secret. And we're trying to figure out what it is. And we are very much open to see things. So I think sometimes that I resent a bit the attitude of these scientists are keeping this secret. I can understand better the government. Maybe that doesn't offend me as much. But the fact that the scientists are doing something that is evil, that is really maybe a portrait of a scientist that it can be found in a book or something. But in reality, we're really normal, curious people that decided to spend a lot of time studying math and programming, and they have a lot of patience to learn new things. And
you've devoted your whole life to understanding
exactly.
these things.
But we love to see new things that we don't understand. I mean, something that doesn't maybe appeal to these things is like, sometimes in the magazine, you see, like a few years ago, we had this strange peak. When we have peaks, you don't need to know what it is, but it means that we see signals. Okay, we see a signal. And then, scientists, they check and check and check to make sure that it's true. We were super excited. In one day, we had 800 papers by theorists written about potential models to explain that thing. And it was Christmas. Okay, it was like a few years ago. So, we're the first ones. So, the thing that are hidden, it's kind of, it's a desire. I don't know why there is this desire. So
people love a good mystery. That's the thing, is people, love a good mystery.
People watch too much TV and too many movies, I think. And then they get this in their head,
Well, plus, I think it's a mystery because maybe they did not study enough in school to see that if you study your course and then you try to do the exercises and then you understand at the end, there's no secret, but you need to put in also a lot of work. Yeah. It's kind of easier to listen to someone talking on YouTube than, maybe do the math. Anyway, it's, I think that also this, it really comes from this, how can I say, misunderstanding between fundamental science and maybe, as I was mentioning, like military science. So there is always this fear that can be, well motivated if you want, that there are very, very specific dangerous things that, oh my God, if they fall in the wrong hands. And this is always what I say. Technology doesn't have a moral. Technology is not, doesn't have, there's no ethic about technology. It depends on the person that use or the use of technology. Okay. So with particle beams, we can cure cancer. With particle beams, we can shoot them sour. Certainly we can destroy our detectors if they don't work.
Right.
But okay, so I think that people sometimes confuse. It's again, it's not, it's a message is not clear. As far as I know, in Europe, by construction, as I'm saying, all the documents, everything we do is accessible. It's public.
Anybody can take a look at it.
Anybody can check it out. Okay. And I've never found anywhere that I wasn't allowed to ask a question or to know something. I mean,
have information.
direct contact with the director of Cern. You can even write a letter to the director of Cern, and Fabiola will answer.
Yeah, and in fact, like, I mean, if you go to CERN's website, they actually address many of these questions that sometimes people have. And I guess I can attest to the fact, I mean, I think I'm friends with maybe 20 or so of you, like, all through these years. And you guys entertain all of my weird theories and conversations when I'm talking about, ghosts or life after death, the near-death experience, all of these things that I find enjoyable and discuss, that I find just on a different avenue of science. I have been very grateful that you guys have never made me feel stupid at all. I mean, we've always had fantastic conversations throughout, these 20 years of knowing many of you, and I can be myself and bring up these things. So Rich, it's very refreshing, because then, I can hear, but I can hear from a different side of it. But the scientists I've encountered have all been open-minded. So I believe that analysis that you give about science, that scientists in general are very open to the possibilities of what else is out there. So moving on to the first conspiracy. So the one was where the woman said she experienced a glitch in her video. So
I remember that one.
Yeah. So I guess the LHC had ran on July 5th when it restarted. And of course, they've referred to it as the experiment, and you've corrected us on that, which I'm so grateful for. But what she said happened was that during that time, she thinks that this proved to her that we live in a matrix, and that running this high energy experiment at the highest energy it had been run up to that point, that it ended up like melding the universe, and then we kind of noticed some glitches. So quickly, do you think that we are in a matrix or simulation, and do you think this theory is possible? Not quickly, just I guess. No,
this is very interesting, because there is like a mix of many concepts in a single thing, and some of them are actually reasonable. Then again, I think that something becomes a conspiracy when everything is squished together and simplified, and then again the words are not used correctly, and then it's difficult to have a conversation.
Right.
Difficult conversations like, are we in a matrix, actually happen among scientists and physicists. I was doing my research before talking to you, and look, we don't know. There's no way to check. Or is there a way to check? So the scientists then, what do they say? Instead of saying, I saw a glitch, I'm in a matrix, they are saying, imagine we are in a matrix. What can we do to check that we are in a matrix? So in fact, there are experiments ongoing to figure that out.
I did not know this.
Interesting.
So I mean, you wouldn't really do the experiment to say, are we in a matrix? But the way that they would present it on newspapers would be that.
Yes, but in sense, what it is
concern, quantum effects, and now you say quantum and everyone gets excited, but indeed there are like specific experiments that can look at behavior of things, that where you can check if they behavior not in the way you expect, kind of like you should imagine if we are in a simulation, then there is someone simulating us. So it has to be like a super mega computer. And we should assume if the computer is infinite, then we can never check it. Okay, so we don't know, we will never know, because it's much bigger than us. If the computer has a limited power, like my computer, at some point
you're going to be able to trace it back to the beginning.
Then if the computer is limited, then you can try to squeeze some phenomena that would be really, really difficult to simulate by the computer. So this is
I did not know this was happening.
Right? It's like, it's like video games, in time, the pixel became more and more like real people. Now you have, CGI is beautiful. It's like, you have movies. Huh?
Yeah.
So imagine, that those are simulation. if we are the same, we are done very, very well. It's very easy to make my hair and everything, but how easy it is to do the quantum behavior of this, you had to simulate all our physics, and maybe, you forget something. So that's the spirit. And again, you see, scientists are fun. You see,
that's crazy. There's some programming in mine I'd like to rewrite. So if you figure it out, let me know.
So this is one thing about the simulation. So really, it's very, very difficult if we're in. Another theory is that the day that we will be able to to do us to simulate us,
right.
And then you see, I'm very fond of artificial intelligence, and I follow that very much in neuroscience. So I'm waiting for the day that we have the thinking machine. I, for instance, as a scientist personally, have this discussion with other colleagues. I do believe that one day we're gonna have, the turning point. We'll see.
Yeah, we
actually fascinated.
Yeah, we actually just talked about a news story in one of our Weird Weekly News episodes about where they've taken pig brains and able to like recirculate kind of bring it back to life. And it was
those are the pigs. I was thinking of the Google AI.
No, for sure with that.
Which is not proven yet. But just to say, so another proof is that the day that we're going to be able to do that, we might be able to find out that we are ourselves a simulation. Yeah,
because in fact, we did talk about that as well with the Google employee that said that, their AI has become a sentient being. So I think with like those two possibilities, when you think about the fact that, with these news stories, they've been able to like regenerate these pigs' brains, and we have these computer programs that are becoming or seeming more sentient, like how will those two worlds marry? That's where my mind goes. So I'm like,
it's fascinating. But then again, you see, this is not a ghost. What I'm telling you is just, normal scientific thinking. I have a problem, I have a question, and I try to make an experiment for it. So then the other thing was about the extra dimension. And then again, they are squeezing, they're hiding the dimension. Well, these things with the extra dimension is also very, very cool, because one of the fundamental theories of fundamental physics, but not the one that is working now, an additional one that we would like, one of those that imagines, new particles and explanation for dark matter, etc. We haven't proven it. We haven't found anything. But if we want to put, things together, then we might have 12 dimensions, of which we only see the 4 where we live in. And they are all kind of
everybody's brains are just exploding right now.
Invisible to us. But I was, again, during the research, I saw this beautiful example to explain to you the extra dimension. So if you imagine that you are like on a, walking on a tightrope, you're a person on a tightrope, then you are on one dimension, right? You cannot go anywhere. But if you are an ant on the same rope, the ant will go around and front and back. So the ant sees more dimension than me.
I can go 360 degrees circumference around that rope.
For instance, yes. So there are other examples. If you are like you have a boat in a canal, and the boat is very big. Okay, so the boat can only go through the canal, and then you have a tiny submarine can go, under on the side and go around.
And go anywhere.
So again, this is the concept. So the dimensions are there. You just know that you cannot see them.
And it's just finding
Nobody's
a way.
hiding anything.
Right.
And we can see maybe particles coming from this extra dimension when we do our experiment, because in the moment of the collision, we have an energy that corresponds to a situation where you can, excite this resonance with this extra dimension, and so see that particle. Keep in mind that particle disappears immediately. It doesn't leave. It's not that I create the new things and then, we have...
And then it's there, right? No, you're carrying around this new particle, baby.
For a tiny moment, we look, yes, they're there. Okay?
Which is why you have the detectors, because the detectors are capturing these at the moment that it's happening, and that's where you're analyzing the data. Is that correct? Is that how?
Yeah. So this is also interesting. This is also a common
Misconception.
Misconception. Yeah. No, I mean, it's true. What you said is absolutely true. But there is something that I also explain to the kids when we explain particle physics. Particle physics is like being a detective, in the sense that, as I said, we create a new particle, even the Higgs boson. Okay, imagine the Higgs boson that we know is there. The field of Higgs boson is everywhere, it exists. But when we make it as a particle, the LHC, it exists for a nothing. Okay, and then it transforms. The correct term is decays, but let's say transforms in other particles that are the ones that make up our normal life. So, the particle, we have quarks and leptons, and basically, we have like 20 particles in total. And of them, there are like 3 or 4 that are the one that make our table, our computer, electrons, and the quarks that make up the protons. Those exist all the time. The other, no. The other ones exist only when we make them, and then they disappear. We don't have top quarks running around. We don't. Okay. We made it.
No, they exist.
So the detector captures the end. It's like when you go to a room and there is the shape of the guy that was killed. It's like you don't see what happened, and then you need to kind of go back from the thing you see. And you say, okay, there's these things. Oh, these 2 things together make this, and this together with that makes the Higgs. There must have been a Higgs. Okay. So it's very indirect. And I think this is also something that it's difficult, it's never really communicated. People feel like you see the Higgs. You don't really see the Higgs. You see the children of the Higgs.
Gotcha. Okay. That makes sense. So you know that that's where it came from.
Exactly. So it's the same with this extra dimension. If we find them, if we see them, then we would see the children of particles that come from this extra dimension that said hi, and
and that's it. Okay, got it. Well, thank you for that.
Okay.
Rich, what do you
think? I think these are the 2 things: the matrix and the extra dimension.
I'm just soaking it all in because it's all real interesting and it makes sense. Just
So our next one was on July 10th. This guy said that he was paying attention to the sky. So he knew about the experiments that were running at Cern, so forth. And then, so on this specific date on July 10th, which was days after, he remembers looking at the sky saying, oh my gosh, the sky looks so different. These clouds look more pronounced, or, everything just looked more beautiful or vibrant, or whatever the case may be. And so he went online and started Googling, or maybe even on TikTok, and looking to see if anybody else had made comments about the sky looking different. And so I guess my question to this one is, our question is, can experiments in CERN cause a change in weather pattern? And I guess the other part of that is, we talked about extra dimensions and timeline shifts. So is it possible that, not only can CERN change weather pattern, can they shift timelines, which we kind of touched on that a little bit.
Yeah. So one thing first, again, to know is that all these people kind of say, oh, on July 5th, at that moment, there was a glitch, or on July 10. So you should imagine that, again, if this comes from the LHC running, which in fact is started running again on July 5th, as is true, then, we do not have like a specific moment when we have we don't have a collision. We make the accelerator run, and then once it's filled, actually it runs for about 20 hours.
Oh, okay.
Then it stops for like 3 hours, and then it continues. And then, so in the period where we're taking data, in fact, it's like a 24/7 type of things until we stop for, over Christmas, there are like 3 weeks break, also because electricity is expensive, or there is something to fix. So the fact that something happens only in a moment is a bit strange to me, because there is not a specific moment that I can fix. And if you think, oh, it's when it's turned on, then the first thing that is turned on is not even at the maximum energy, because we always start little and then we keep, it's like when you have a new car. You always, you go slow in the beginning and then you.
Or even starting it in the wintertime with older engines, sometimes it has to warm up. So I think it's the same concept.
It's a warming up, right? So it is a bit difficult for me to attach. I saw a glitch with these things. While, like the opposite is kind of true, in the sense that the machine, for instance, when it was running with electron and positron at the LHC, there was this very famous effect that the machine was seeing when the TGV train, the fast train was passing by. So there was something funny in the measurement of the physics measurement. And at the end of the day, it was brought back to the fact that there was a train passing by once a week or something.
So while the experiment was running, you were able to pick up other things going on versus.
Exactly. So the experiment was so sensitive that the outside was influencing the beam.
Versus the
beam influencing the outside.
Everything on the outside.
Just to give an example of what it means being very, very sensitive. So these beams are powerful, but still the LHC is like 100 meters underground. The whole thing is shielded in concrete, already, outside the tunnel, we do not have effects from the beam. So I think it's so fragile that it's very difficult that it makes a macroscopic effect outside. I mean, of course, we did have a huge accident in 2009 where one of the magnets exploded. There was a faulty connector, okay, and so then this thing is like almost at absolute zero. So the faulty connector started warming things up, and then liquid helium doesn't like to be warmed up, and then it increases the volume by, I think, 800 times, a lot. And so there was a huge thing. So that, yes, was an effect.
But it did not affect the outside world.
So because the whole tunnel, these things that are huge, these magnets are 15 meters long and they weigh tons, and they were just flew, in the tunnel. So yes, that. But the fact when it's running in normal mode, practically impossible, in the sense that is a question of safety. For the LHC is built in a place that is very inhabited. It's a city.
Yes.
Okay. It's not. I mean, even Fermilab is more like countryside.
It's not in the middle of nowhere, though.
It's not in the middle. It's actually in the middle of a very populated area. And so the security for the population is very, very high. And in fact, making sure that the population is not afraid, it's one of the things that we are committed. So most of this question, in fact, come from me, when we talked in meetings to the population itself before we run the LHC. There are town meetings with people where they ask, it's like, my kid's school is here. Is there a problem?
So sorry, but to go back just to clarify the answer on this. So essentially, when the machine, I guess, was already warming up prior to July 5th, correct?
No. July 5th started warming up.
Okay, so July 5th it was.
I'm just saying that it started warming up. It would have been much less than when we turned it off 3 years before. And so why the lady didn't see anything 3 years before either? I mean, there's nothing special in that moment of high energy in that specific thing to say, oh my God, a glitch, because I've never touched this. You see what I mean?
Because, so I guess it's important to point out then, though, so the machine was turned on July 5th. And so
it's true that on that day, we turned on a machine. And so the beam started circulating.
Correct. Yeah.
And the experiments, I think, turned on a little bit later, because first we want to make sure that the beams are safe and they are okay, safe for the detector. These beams are not dangerous for us, for the people, but they are very dangerous if they happen to go, outside their tube and maybe into one of the detector, they would destroy it.
Okay.
It's all very, very delicate. It's like you have this huge, kind of building.
Right.
A detector is like a building. It's like a 3 to 5 story
Right.
building. Okay. But they are extremely fragile and extremely expensive.
Right.
So if the beam goes into that because we make a mistake, and we can, okay, just to give you the idea why we make a mistake, again, orders of magnitudes. This is 27 kilometers. I don't know how much is in miles. 7 miles? No. 8,
somewhere around there.
I don't know. So some 10 miles, imagine. Okay. 27 kilometers. And you have beams that are like a needle
16 miles. Yeah.
16 miles. So you have beams of the size of the head of a needle. They need to come together, okay, at the speed of light and 400,000 times a second.
Right.
So that is difficult. It's a needle that needs to do 27 kilometers and you need to find the right position.
Right.
Hard.
So yeah, that's what I wanted to clarify. So essentially what I was getting at, and I just probably didn't explain it well, is the machine started on July 5th. After that point, these beams are going around the Collider. And so how many times, I guess, so to get to my point, I'll ask the side question. How many times do the beams collide during any given experiment? Is it multiple? Is it once? Is it
like 400,000 per second, even more maybe now?
So there's a collision.
All the time.
Okay.
Constant.
So that's what I was trying to so that's what I was trying to bring to light for people that are wondering about these conspiracies, is the fact that the machine turned on July 5th and the people are making these claims, but where the real energy comes from is these beams that continue to move around the collider at the speed of light and then colliding, and they're colliding multiple times.
All the time.
So if we were going to see these types of changes, we would just continue. All the time.
Yeah, I mean, every day someone should see something or say something, right? This is what
they're associating it around this. Yeah, so they're associating around this one event on July 5th without understanding that this is something that has continued to go on since July 5th, and we haven't heard anything more about it.
They're assuming that the turning on part of it is the major power point of it, is what they're assuming, and that's causing something, and that's just not the case.
Right. Yeah, and this is also the communication on the newspapers, because they say, oh, the experiment is started today. And so then if you don't know, and of course you might not know, because this is a very specific thing, you might imagine that there is like a punctual specific moment when things happen. Or like when they say, when the Higgs was discovered, now, I'm kind of jumping around. There is this thing of the portal and the Higgs, etc. So again, one needs to know that when we say we discovered the Higgs, this is another interesting concept, statistics. I don't know how much you like statistics in school, but we do statistics experiments so that we collect a lot of data. We look at all the children, of all the collisions that we have. So there is a lot that we know. And so we have our simulation and we know how they should behave. Then there is a new particle. We have the simulation. We think, where it should be, the Higgs. In general, we try to make plots that are easy to understand even for us. So maybe there is a peak. Okay, we see that there's something new that builds up over the thing we know. We also like to see that, we like to see that. But at the end of the day, when you take the plot, and it would be nice, I should have prepared maybe those images. There is the famous image of the Higgs discovery was shown at the Nobel Prize, whatever, and there is a peak, with some events. We do not know which one are really the Higgs one by one. It's a statistical thing. We know that all the events that end up being in there have the behavior of the Higgs. Okay. Of those, 90%, now don't remember that peak, look like the Higgs, and we know that there should be 10% from something else. Now, depending on the situation, doesn't matter. But of all these, sample of events, we have a mixture of something that are the real Higgs, and some we call it background, something that mimics the Higgs very, very well. We do not know which one it is. So we will never know in which day and in which moment we produce a Higgs.
Okay.
You see my point?
Yeah.
I
So
cannot tell you that day I made a Higgs.
Or that time or that moment that we could correlate with any of these events that people are claiming going on.
Exactly.
So I guess I want to move to the safety issue you have brought up, and just if we can quickly touch on that, is that you did mention that these are built very far underground, and people are saying, oh, it's because it's so dangerous, so therefore it must be dangerous. So you did let us know that the biggest danger is to the machine, not to the population at large, and that safety is a huge issue. So is that why they are built so far underground, is to protect the machine, to expect the
Well, no. The underground is also for people, because at the end of the day, these are beams of particles, very energetic, and you want to make sure that. So what happens is that you make all the objects that are in contact with this beam and all this kind of radioactive, and you can have everything is very, very shielded. But you can have, again, as I said, accidents, the beam goes out. It can happen. It has happened in the past. You want to control it, but you want to make sure that it doesn't, it's far, far away, very far away from anything that could happen to people. Okay. So, again, like even when you go visit, when you go to see the experiment, you can, in fact, come to Cern, and you can come to one of the experiments like CMS, and you can take an ice elevator that brings you down 100 meters. But if the machine is running, we're taking data, then we cannot take you, or I cannot even go in the tunnel or in the experimental cavern, because it would be radioactive. It's not good for anyone.
And it's radioactive because, I guess, explain to the listeners who wouldn't understand why it would be considered radioactive.
Yeah, because you have all this strong interaction of particles with the material, and every time then you kind of destroy like the nuclear fabric of matter. When you have things. So radioactivity, you're familiar with radioactivity because we have also natural elements that are radioactive, or isotopes, and what it means that they decay, they change, and they emit stuff. But you can also make matter radioactive. You can activate when you have this type of energy going around. So we, it's activated. So everything that we use in the cavern, for instance, when we have to take things out, you need to be careful. We're never allowed close to anything that would really be a danger to a person. And we also take a lot of safety courses and everything. So it is extremely safe. I mean, nothing ever happened there. Okay.
And so the tunnel is built underground for the safety of just everybody involved, just due to the nature of the experiment.
Yes. Okay. And also, but not only, it's not just safety. I mean, here I said it's a very populated area. We cannot have 27 kilometers, and how do you do traffic, or do you go? So that also, it's a practical thing to have it below ground, and then you have also all the isolation, because it's cooled down, it's cooled to the absolute zero.
Yes.
So, and again, and then it's also less exposed to this is also something that doesn't come out often in this, but people are not familiar with. We have particles all the time that come from space. I mean, we have something that is the atmosphere that protects us a lot, but still we have particles coming all the time. And in fact, we see them in the experiment. And also, being below that also kind of screens also that. At Fermilab, it was up. At Fermilab, it wasn't below ground, but we had the space. I used to go skating around the ring.
I rode my bike in there many times.
Yeah. So I mean, it's safety of people up to a point. I mean, there are future collider, for instance. This will make it fun for conspiracy. So one of the next machines that we want to build, especially in the US, is very popular now. It's a muon collider. So the electrons.
Yes.
It's like a fat electron. Okay. So that's good because we can make it small for many, many reasons. I don't go into physics. But the muon has the characteristic that it's not one of these particles that lives forever. It decays in something else. And when it decays in something else, it emits also something called neutrinos. There are particles that you don't see, very, very tiny, but then there would be a lot. And they can also be a radiation danger. And so a machine like that, for instance, at the moment, one of the idea would be to do it 500 meters underground so that we don't get the neutrino. So there are these type of issues considered. But yeah, no. So 100 meters is a mixture of people, logistics, and machine practicality also, because going much lower, it's complicated, and it's difficult also for the safety of the people working down. I mean,
yes. Well, thank you for answering that, because I just want to make sure that was clear, because we did talk about that in last episode. Okay, I'm going to switch gears a little bit to less scientific things, but I think that you can.
There was a time thing also that you mentioned there.
Oh yeah, did you want to speak to the time?
Well, yeah, maybe just one thing, in the sense that because it's similar to the matrix. It's like, do we know that we are in the matrix? Like, do we know? Okay, we changed the timeline. What does it mean?
Right.
So the thing is that I just wanted to make the comment that if you are in a timeline, you don't really know. You cannot really measure. Again, it has changed. So it's very, very
similar to measuring if we're really in the matrix. It's hard to measure. Did that really happen?
Yeah.
I would love to have you on for another episode to talk to us about time travel, because that's a whole other topic I would love to discuss with you. What do you think, Rich?
I need a DeLorean first if we're going to talk about that.
Exactly.
And a flux capacitor.
Apparently you need a very fast car for time travel. So
very fast.
Okay, so now we'll jump into the other thing. So now there was a user that had said Cern, along with some other larger companies, are satanic and demonic in nature. They said that the logo for Cern is actually 666, like melded together in these weird ways. Which of course we know that is considered the sign of the beast or the devil. But so this user went further on to say that there's a statue of Shiva, if I'm pronouncing it correctly, which is the Hindu god of destruction. And he likened it to the equivalent of having like a statue of Satan outside of a building. Like that was the equation they were putting together, saying that Switzerland is only about 1% Hindu, so they couldn't imagine why the statue was there. So what I found in my research, though, is that Shiva is actually about destroying the universe to make it a better place, like for a better change, which I find symbolic personally with regards to the work that you're doing with Cern. You're trying to essentially recreate you're deconstructing things so that you can figure out how they were constructed. But I don't take that as meaning like you're going to destroy the universe to create a new dimension, and that's what so why the statue, I guess?
No. So the statue, which is really beautiful and it's next to my office, it was donated by India to Cern. It was a donation.
Beautiful.
And then the choice of Shiva is exactly for what you said, but because it's called the cosmic dance. And so this is not the destruction, is the alternation of destruction and construction. It's the alternate.
Yes.
And in that, then I found, now I don't have it here, but then basically there is also like a sentence. I don't remember. I've not been next to this studio in a long time, but basically there is a phrase. There are phrases taken by don't remember. One is a physicist and one is a writer or philosopher that kind of remind to explain that. I don't know if they are on the statue or they just go along with the description of the present. But the idea is that it's destruction and rebuild, and it's a constant making and unmaking, which is the fabric of the universe, because it's the evolution.
Right.
So I mean, yeah, it can be.
I think it's a beautiful gesture. So, but
no, and it's I love it. I mean, it's really beautiful, and
so what about the Cern logo 666? Do you know how the logo is made?
So that I heard a lot, and so just to say, what looks like a 6 is to remind people of the colliders, right? Because they are round, and then they have an injector. There is always, this is a circle, right? And how do you bring particle in that circle? So you make them somewhere, and then you have to transport them there. So when you make the drawing,
yes,
like
I'm actually gonna show. I'm gonna share my screen really quickly for those that are watching on YouTube, just so that they can see what we're talking about here. So sorry, are you able to see that, Patrizia?
Yeah, I can see that exactly. So here you see in the if you take the bigger one or whatever, you see that there is a circle, and then you have different straight lines going in the circle. Okay. And so in fact, in this case, this can also be interpreted as we have one line to the left of the particles going in, and then at the end we use the beam, instead of being a collider, then we use the beams to make other, as I said, at Cern we make many
you repurpose them to another experiment.
So one of the type of experiments that we can make, it's not having the beam one into the other, but it's a beam going onto a target, and then with another detector after. So you extract the beam. So effectively, that's the drawing, and then you send it to somewhere else to do another experiment.
So it's basically like a blueprint of how the
accelerator system works. Gotcha. So it kind of looks like 6.
So it's not a 666. Okay, so you're not all worshiping the devil.
I don't think that they thought about. I mean, if you look, there is the same concept with the Google Chrome. I think they say the same thing, that it looks like a 6.
Well, thank you for entertaining that. So one of the last things that we're going to talk about here is the Mandela effect. And in the first episode, we talked about the Mandela effect. And I think that we've already kind of covered a lot leading up to this last thing. So I guess I'm going to find out what you think about the Mandela effect. So just to recap, the Mandela effect was born from a woman that thought that Nelson Mandela had died while he was in prison in the 80s. And then later he actually had died in 2013. At some point, this woman had found out that he was alive during this time. And she's like, oh, but I thought he died. So she started this, she called it the Mandela effect, where she started noticing things around her weren't exactly what they seem or how she remembered them. And then we gave a list of all the different Mandela effects, like remembering certain things about products or services, those kinds of things. So you took a look at it. What do you think of this theory? Do you think it's how we said, scientists saying people are just misremembering, or?
So if I speak for myself, my memory is very bad for this thing. So
you have two people joining you with the same problem.
So I would agree. And especially after COVID, I think really my memory is playing lots of tricks. Yes. So personally, I cannot say much. I mean, I think that again, if you want to be scientific, one thing that is interesting is how many people kind of agree on the same effect. It's like, oh yeah, Mandela, and so many. Now, again, when you're a scientist, you don't never count the positive. You need also to count the negatives. So it would be interesting to measure, but we can't. Right. To have an unbiased set of the population and try to check with them how many instead remember correctly or remember different things. So my opinion on this is that
you guys didn't switch the timeline.
I do not have the data. With this type of data, I cannot make a conclusion.
You cannot extrapolate a good conclusion on this.
I cannot make a conclusion because again, this is like this is also the problem with many things, where then there is this fracture and difficult discussion, tension between conspiracy people, let's say, or curious people, and the scientists, because it's somehow there is this need for okay, this is the truth, this is the answer, for quick understanding. And in general is not. I mean, science takes time. Science changes their mind. The measurement improves, and maybe the result changes. It's not that the scientist said something wrong. It's just that the more you know, and you might change your mind. So in this case, it's a bit, like I'm seeing this.
Data.
Everyone that agrees is gonna say I agree, but the one that don't agree are probably not gonna comment on that.
Yes, so incomplete data, I get it. And we kind of touched on a lot of that. Rich, what questions do you have for our guest?
I don't know that I have any further questions. My mind is actually just overloaded with all the information I have.
Comments, concerns, did you?
I think I kind of expected most of what the answers were going to be, not because I'm a scientist or any type of science geek, as
we
you
just
say,
play one on a podcast.
I just, it's very interesting to me, and it kind of goes to show that when people that don't have any idea, just like the guy with the clouds and the weather, if you actually dig a little deeper into it, you can make sense of a lot of the things that people have concerns about. So I don't know. I thought it was very interesting. So yes. I would love to do a virtual tour. So
yeah, you can. You can book it, and
or we can just fly there. I mean,
well, that would be better. That would be more fun.
Field trip. All right.
Yeah, I'm surprised that you haven't said anything about the movies. I know, but the one at Cern, because there is the famous one of the statue, right?
Oh yes, and so,
but there is another one that is very nice.
What is it?
I think I told you, the one with the zombie.
Oh,
this is a very cute movie. You should watch it.
All right.
And this is good for everyone. This is done by students, and it's called Decay.
Okay. And, I should post that. That's right, because CERN had their own. Yes, I remember this now. So we'll have to post that, Rich. It's a movie, and if I'm not mistaken, it's done by the students there. Yes.
Okay.
It's an amateur movie that plays around conspiracy of course it's a fun thing, but it's I mean I think it's also good to see again the open-minded scientists. Okay, we are aware of doing things that are very special, that are very difficult to understand, and there is the ability to to invent scenarios and to do other things. I mean, we also didn't talk about antimatter, which is another fun thing.
We could go on and on. Okay, I think we're just going to have her back for a whole other. We have 2 episodes. We need to try to get
part 3.
Yeah. Or we just totally go into the whole other side of CERN that's aside from these conspiracy theories and try to understand CERN better and the experiments. So that would be something we'd love to talk to you about on top of the other. So we would love to have you back. So, maybe sometime in the near future, we can definitely do another episode and not focus on the conspiracies. Or you know what? Patrizia, you said something really interesting, and I think I would like to adopt it. You said you started to say conspiracy theory, and then you said, or the curious theories, and I think that is a really respectful way to put it. Is saying it's the curious theorist is I think is a more respectful. We want people to question things, so. Right. On that side of it, maybe we just focus more on what's going on in CERN, but I appreciate your take on that, because it is a very respectful way to say to people, all opinions and questions and, concerns are welcome. So,
yeah, no, I think that one thing that sometimes is difficult, honestly, is that, there is this curiosity, right? It's like, you're not telling me everything, I saw these things, I have the Mandela effect, you're not listening to me or whatever. And it feels though that there is much less open mind on the person with the theory,
right?
Open for discussion, than on the scientist side. So that's also why sometimes there is the tension coming up, because again, so many things. As I said, science, it's exploration, it's evolution. We just went through a very difficult pandemic period where all the scientists, me included, have been really on the spot. I had to talk with a lot of people, have very nice discussion with a lot of friends. Honestly scared. We were all scared.
Right.
Nobody has the truth in their hand. We didn't know these things. And I think sometimes it's not recognized that science, it's slow. It takes time. It takes checks and checks and checks. And it's not because you want to be secretive or, dismissive. Is that sometimes you really do not know. And admitting that you do not know is not a shame. It's the way to learn. And so sometimes I think these people that attack scientists, and let me just say my pet peeve, they should be more, have more humility and recognize that they're curious and that they are searching, and maybe they are searching on some sources that are not as checked as others. And there's nothing wrong with that. Good, check. But then if you find that maybe your source is not valid, be open to change your mind and evolve.
That's a good point.
We all do. So that's just
and that really can be translated in anything in life. So I think that's a beautiful synopsis on that. So I guess before we go, one last thing, is there anything else? You did such an amazing job telling everybody, about the experiment, about, what you've done and the things that science is doing within CERN and the scientific community. So is there anything else that you would like the public to know about either the Large Hadron Collider, CERN, anything, like any closing statements you'd really want to drive home?
Well, I think, one of my closing statements I just made, and is this open mind on all sides.
Yes. Let's
all be open. Let's all be patient. I really feel that this is a period, this is a time where we have so much communication, so much information. And by the way, the web came from CERN and the internet.
Oh, I did not know that. Oh my gosh, we have so many things to talk about in another episode.
I knew that. I knew that. I did.
We just celebrated 30 years. So we gave the world that. And so it's kind of funny that then that is used to make fun of us, like you're hiding things. I mean, we gave you TikTok.
We gave you the model by which you could search all of these things.
Exactly. So in that
as a joke, you should just turn it off one day. Boom. Oh, just kidding.
And now it's out, and now it's out. The beast is out.
We'll return back to the office. People can calm down.
Exactly. So and this was a project. It's very interesting. You should look it up. Because the guy worked on this project in the weekends, off hours, and when he told his boss, the boss said, "Well, this is vague but interesting. Okay, I can give you this machine. You can do it off your office hours." And that's how the guy.
That's how it was born.
Tim Berners-Lee then developed the first setup that then developed. So. Wasn't even taken that seriously. So this is what I'm trying to say, that every time we learn, every time we evolve, so we really need to be open-minded. We have so much information. It's so hard to figure out what is true and what is not true. So I think it's very, very important to follow the sources, be very calm in discussing, listen to people that maybe have more experience than you. It's also not necessarily because someone is a scientist or has a Nobel Prize that they have the truth, because there is a lot of scientists that are doctors, physicians, Nobel Prize, they say things that are wrong, because life, we can kind of just lose it.
Right.
It has happened. It happens all the time. So really, sources and talking openly and calmly then can go a long way. And then maybe we do discoveries, because I'm a yoga. So this is long maybe, but just to finish with one of my favorite things.
Absolutely.
In my yoga teacher experience, I've been studying a little bit of anatomy, I'm not, a medical trained person. But I discovered the story of fascia, of all our connective tissue. And this is a beautiful thing. I mean, until few years ago, when the doctors were studying a body, they would open it, remove the connective tissue, and study the rest.
Right. Without thinking the disease that can be brought about by.
Without thinking, it's like, why do you throw all that away? And then now that we have better machine, better things, and people started thinking, oh, look at that. And then you discover, oh, but the nerves in that thing. Oh, but that transmits so many things. It's so important. And it's like, hello, we were throwing it away. And so were the scientists mean? I don't think the doctors were mean. It just, you learn, you try.
They weren't trying to hide anything. They weren't trying to be any way. They just, that was the point in the scientific journey. And I think every day it grows. So
exactly. So open mind.
Well, thank you so much for joining us today. I hope you had a good time. I hope you'll consider coming back again and talk about all the cool stuff. So, well, thank you everybody for listening. Remember, join us every Wednesday for some lighthearted, weird weekly news that we bring you a couple episodes each and discuss it. And then every other Monday for our single topic episodes. So until next time, stay weird, everyone. Ciao.
Thank you.
Ciao. Thank you.
Bye.